just message the
Oh, okay.
okay.
I see. Okay, so the topic for today is two-level type theory. And first, let's review what we have seen in the previous weeks about Preshift models. Okay, so the assumption is that we have a category C. We have a category C, and we get a model of type theory Preshift over C. And this model has pi types, sigma types, universes, identity types, most kinds of inductive types, including natural numbers and booleans and so on. Yes, and then different base categories are useful for different kinds of things. And I think we have also quickly discussed, but not in depth, that if we start with model C of some type theory, and we'll give it a name T, then Preshift of C will also be a model of T. So the category of Preshifts can be extended to model of this type theory T. But now Preshift, this category of Preshifts is both a model of T, of this type theory T, and a model of extension type theory. So it's a model of two type theories, and these two models are different. And what we do when with two-level type theory is see these two models as a single model of a larger type theory that has two levels, one for T and one for ETT. So two-level type theory, we say that it has inner things and outer things. And the category of Preshift over C will be a model of this two-level type theory, where the inner things correspond to the model of T, and the outer things correspond to the model of extension type theory. And what why is this useful, or what are the applications of this? One of the original motivations for the introduction of two-level type theory is that can make, well, so some constructions that will typically be done externally can now be made. So if we have a model of a type theory and we make some construction on it, well, for some of these constructions, we can now do them in the model presheaves of C instead, in the two-level type theory of this model. So well, some external constructions on model C of this type theory can become internal constructions in presheaves over C. And well, performing these constructions internally to presheaves over C will make them nicer in some way than the external constructions. Well, so it's more or less the same thing, but this can be yeah. So two-level type theory can be used for metaprogramming. So I think András gave a talk in a type theory seminar about 2 months ago about this. Well, the idea is that if we only evaluate the outer level of two-level type theory, we get types or terms of the inner layer level. And if you yeah, also two-level type theory and presheaf models can be used to interpret higher order abstract syntax, which means that which provides a nicer way to this provides a way to perform constructions over C. Without explicitly dealing with substitutions. Okay, so I think now I can define the components of these models. So maybe we can start with the components of presheaves over C as a model of ETT, of extension type theory. So the contexts, the set of contexts is the set of presheaves over C. So and the presheaf is factor x from COP from COP to set, and if we unfold this, if we unfold what this means that we have for every object I in C have xi the set, and for every f from j to I. In C, we have xf from xi to xj with the compatibility with compositions and identity morphisms. So that's x id is id from xi to xi for every I, and x at the composition of f and g. It should be the composition of xf and xg. I just need to check the if it's not in the other order. I, j, k. It should be right.
Oh, I think it's the other order, because if you write it with the postfix notation, then you don't need to swap. But now, then, because this is now prefix notation, you should have to swap.
Yeah. Yes. Yeah. Well, I'm also confused because I usually use the diagrammatic composition order. Yeah, that's it. And then the morphisms of Ricci of the substitutions of this model from x to y. It's a set of natural transformations from x to y. It's should be the name for one. Okay. F in sub xy will consist of a function fi from xi to yi for every I. In C. And such that for every f from C from j to I, the square where we have it's from j to I. The square that we can make with the FIs as horizontal rows and the YFs and XF as vertical rows commutes. All right, and then the types and terms of this model are just dependent variants of this. So the types over X is the sets of dependent sheaves over X, which means that you have for every I in C some yi from xi to set, and for every f from C from j to I, we have some yf from from yi to yj for every x in yi. Yeah, and I will omit the naturality for terms. But a term we have for every I in C, some function. But y is not a good name. Yeah, ti from x to y. Yeah, so this was the Presheaf model, the Presheaf category. And one of its, well, and yeah, one of the most important things about it is the unit lemma. And the unit embedding. So we have the unit embedding y, but that's a functor from C, Presheaf over C. And the unit lemma says that for every I in C and x in Presheaf over C, we have morphisms or substitutions from unit I x are isomorphic to x evaluated at I. And then we can also look at the dependent unit lemma, where instead of a Presheaf, we look at a dependent Presheaf or a type of Presheaf model. So if we have this will be for every I in C and x, the type over unit I, we should have terms of x at terms of x should be the same as the evaluation of x at I. And now, because x depends on unit I, we need to provide something where, when this something should be in unit I evaluated at I, which is known to be the set of substitutions from the set of morphisms of C from I to I. So we can just use the identity of C at I. And the point is that yeah, so now I will look at Presheaf C not as a model of EDT, but as a model of some type theory when C is a model of type theory. And actually we have a bit more. We also have the unit embedding will be a morphism of models of T. So that this will be a morphism that embeds C into precious over C, but it will also be more. Will also have that this unit embedding will be isomorph bijective on types and terms of C. And actually, I think if we just try to construct this model from this, it should be possible. I don't know if it uniquely determines the model, but maybe it does. But maybe let's look at what this means.
But isn't it a weak morphism of models, right?
No.
Or is it a proper morphism of models?
It's a proper morphism. No, it's weak, yes.
Okay. So it preserves context extension up to isomorphism, right? Yeah.
Yes. So I need to fix notation for the types and terms of C. So we have okay, so let's say that the types and terms of C are denoted by type C and TMC. And actually, so type C is a presheaf over C, and TMC is a dependent presheaf over type C. So we can say that type C is in con, so that's the objects of the presheaf model, and TMC is in tie. Hopefully this is not too confusing. Yeah, so I
would write. Yeah.
Okay, I can do this. It's a bit heavy, but it's not. At least it's not confusing.
And write instead line 68. You should also write type C in the end, 60.
Right? Yeah. Okay, and then we want UNIDA to have action. The unit embedding to have actions on types. So this will be a natural transformation. This will be for every I in C, type of C at I, a type of the model, and terms. This will be for every I in C, and type A, a map from terms of type A to at I to dependent presheaves over this action of UNIDA on types. Okay, and we want to have we want this action to be bijective on types and terms, so we want this to be an isomorphism. Yeah, I need to say that this is at unit I. Okay, so we want these to be isomorphisms, but now if there's an easy way to achieve this by using the unit lemma and the dependent unit lemma, because so no, this is well, that's not what we want. No, we want yeah, okay, so what we want is we want to define we want to define TC and TMC into Preshift model. Yeah, so this will be yeah, so this will be a Preshift over Preshift of C, and this will be a different Preshift, but between yeah, so this is in Preshift over Preshift, so this is a bit confusing. But now what we want is this and not what I had written previously. Okay, but so if we use the unit lemma, so that the types of C at Y is the same thing as substitutions in the Preshift model from unit I to the Preshift of types of C. So what we can do is say that types of C over Preshift over C at any Preshift X will just be the substitutions of the Preshift model from X to tie C. Can align. You can do it like this. So we define it to be this. And so if we define it like this, then by the unit lemma, we will get this isomorphism. Yeah, and now we'll get something similar here. So this should be the same as terms over unit I of type TMC, but now we need to see TMC as something that is over. So we need to see TMC as a type of the Presheaf model over unit I. So this will not be exactly TMC. This will be something like TMC over I. Well, so this will be TMC somehow at A. And this will be a Presheaf over unit I. And if we have some F here in unit I at J, this is defined to be the actual TMC at J and at A substituted by F. Again, then if we...
But sorry, I don't understand why do you have separately TiC and TiC in Presheaves over C?
So
why
well,
should they be the same?
So TiC, we want to give
or one of them is a term or what? Or
we want to extend Presheaves of C to a model of the type theory T. And for now, we only know that C is a model of T. So, but first we need to define. We need to define the types and terms of this model of over Presheaves over C.
Oh, I see. Okay. Okay, and then types. Okay. But I mean, aren't types okay by definition? Because, sorry, I need to. Oh.
I think it's maybe a bit confusing because on line 67 and 68 we have TiC and TMC, but those are just the types and terms in C. Oh. And now we are defining TiC and TMC, which are the C types and C terms in the Presheaf model.
Okay, I see. Yeah, so maybe for me it clarified if I write down explicitly the types of line in line 71. So what it would so it has 4 components, and then what are the 4 components of TMC of Presheaf of C? That
at
least that helps me to understand what's going on.
You can say that we have TiC if X is the complex of the Presheaf model, and this gives a set. And for this one, if X is a complex of Presheaf model, and A is in this one at X, we get a set, and we also get some substitution compatibility, some restriction operation if F is a substitution of the Presheaf model from X to Y. We get something from this at Y to this at X, and also have one for terms. Right, so this is, and we can also, maybe I can say that this also has two components. So this is for I in C, we have set. And we also have some substitution operation. And this one, I in C, and type over I, we have a set of terms, and we have some restriction operation. Okay, so these components are over C, and we want to define components over presheaves of C. And we can find so we can use this definition for type, and by the unit lemma we get some isomorphism here. And for terms it's a bit more complicated because we first need to we actually need to define the dependent presheaf over which we apply the dependent unit lemma. And it's defined here, but I don't know if it's clear. But then we have such a presheaf, and we can define so this should be yeah, it really needs like this. We can define this to be the terms of a presheaf modular C of, so here we need to generalize from representable presheaves, so presheaves of the form lambda I, to all presheaves. And here we need to do the same, and it's so it's easy for the first component because we just replace it by any presheaf, and then we also need to generalize the second component, but then it will not be so the types of A here and here are not exactly the same, but it's possible to also define something like this. When here A is in this, so this means that A is a substitution from X to type C. Well, and actually this will just be so if we have X in X at J, this will be terms of C at J at A JX. Yeah. And these two things are the same, or are at least isomorphic. when X is Uneta I. Yeah, so okay, so maybe doing this computation was not. We can do this computation on paper, but then it's not probably not easy to understand it if you just sit like this. So anyway, what do we have now? We have well, we have what we want. We have y from C to Cauchy over C, a morphism of CWS that is bijective on types and terms. And then if you want to define the to define the pi type, the type formers and term formers over precious over C. Well, we essentially have to look at the definitions, at these definitions, and then it's not very hard to define them. And this will also this morphism will also be a morphism of models of T. Okay, so this quickly becomes confusing if we look at the definitions. What we can do is look at two-level type theory, and in order to see what is available in this model. So what we have in two-level type theory, or well, what is the model of two-level type theory? First, we have model C.
Sorry. So
Yes.
here we have this Yoneda embedding is a morphism from C to Presheaf C, and it's bijective types and terms. And so if you want to interpret any type former of C in Presheaf C, then we are already done.
Well, not exactly, because it's we're not yet done, because there may be some because this one has more contexts than C. So if you want to interpret type formers in contexts that are not in the image of a Yoneda embedding, we are not. I mean, it's not completely obvious.
So you say that, so if I have any type in C, then I can do the Yoneda of the type. But then the problem is that the type that I get is only in a representable context.
Yes.
Okay.
But yeah, and then of course we'll be fine, because to define them we have only looked at things. Somehow we have obtained these definitions from looking at what happens in a representable contexts. So of course we'll be fine, but we cannot.
Yeah, I mean, I see that
we cannot take the shortcut here.
Yeah, I mean, so here in the definition of TIC and TMC, we move from the TIC to TIC of X. But this is, so that is there a way to abstract over this step when we say that we move from representable context to any X?
Sorry, which step? This?
Yeah, because we have a TIE CI and then we have a TIE CX, and as I understand, I have to do a similar kind of generalization step when I want to define any other type former in the PreShift model.
Yeah. So yeah. So I don't know what is the shortest way to make this general. I know that essentially what happens is that we define these things using the so we can use it. We can use a big Y for this. We have big Y from PreShift over C to PreShift over. No, that's not it. So if we have Y from C to PreShift over C, and if we look at that's Y lower star, we automatically get some functor from PreShift over C to PreShift over C. So this functor can be obtained from any functor from any C to any D. We get a functor like this from PreShift over D to PreShift over C. And if we apply this to the Yoneda embedding, we see that this functor does exactly the the main component of this construction is applying this functor. And this functor will be a morphism of PreShift models. So it will be a morphism of CWS for the usual CWF structure on PreShifts. And I think we can use this to make this work nicely. So we should be able to use this to just say we use this functor, and when we have anything, we just apply this. This functor preserves maybe at least sigma types and the pi types, and just from this we should just this should automatically provide a way to do this construction for any in all possible cases. Yeah, sorry, this was not very clear.
Okay.
Yeah, I guess my main claim is that this functor is the main step of this construction. Yeah, so model of two-level theory is first, well, so it's the category C. With a terminal object, or this means with an empty context. And with the structure of a model of T, the structure of model of ETT, this one, and for also give the components for each of those. So this one has tie. Okay, this will be inner types. So that's inner types, inner terms, inner context extension, and so on, and maybe some type numbers. Maybe you have inner pi types, for instance, and inner sigma types, depending on the type priority. So this is the inner local, and this is the outer one. And there we just have the same, but for outer things. Okay, well, so far there's no relation between these two models. And the only relation will be that we have these additional components. We have iota for every context, and inner type, we get an outer type. And we also get for every context, and, tau and type, we get an isomorphism in between inner terms of type A and outer terms of type iota of A. Okay, but so yeah, and so these are the only two new components.
Write the gammas here in type.
Yeah. Thanks. So let's look at what we can do with this. For instance, if we have, well, okay, let's fix the context gamma, and we have some inner type of gamma and some inner type. Okay, maybe something. The first thing I can say is that this implies that we can get an isomorphism gamma extended by iota of A is isomorphic to gamma extended by A, where the first extension is an outer extension and the second extension is an inner extension. In particular, we don't really need inner extensions. We can just always use outer extensions. Yes, for example, let's look at an example. If we have two inner types, we can form the inner pi type pi I A B, and we can form the outer pi type pi I iota of A iota of B. Also need to look at the types of iota of A and iota of B. And yeah, this should be some outer pi type. Okay, but okay, so there's so this is not exactly well typed because of this isomorphism. So the second type given to an outer pi type should be over gamma outer extended by iota of A, but we have this iota of B in gamma extended by A. So if you want to be fully precise, we can use this isomorphism, or we can just assume that this isomorphism is actually an equality, and then things become simpler, and we can write this. So I will omit these isomorphisms, and we can also omit the isomorphisms tau. Yes, we have this inner pi type, and it's an inner type, and we have the outer pi type, and this is an outer type. And now we can wonder, are there equal or isomorphic or not? And well, actually, so we can prove that they are isomorphic. So we have some isomorphism between terms of the inner pi type and terms of the outer pi type. So maybe let's define this isomorphism. Okay, so in the first direction, if we have some f, in here we can look at the application of f. This will be in B over this context. Okay, then we can substitute or assume that this is an equality to get something with an outer extension. And also this was the inner application. And now we can use the outer lambda to get so first we can replace this inner type with an outer type of type iota of B. And now we can use the outer lambda to get some outer element of the pi type.
But lam O of up I of f, not simply f.
Yes. so we can go in one direction. I guess and because well, at every step we have an isomorphism, so we can compose all of these isomorphisms. Okay, but so why does that work? So so you can see that to go in one direction, we needed to use so we need to use the elimination rule for inner pi types and the introduction rule for outer pi type. Right, but so this works for pi types, but this will not work for all types. I guess I can say that as an exercise, we can prove that this works for sigma types. But we can show that this does not work for natural numbers, for instance. Okay, so if we have n some external natural number, some outer natural number, then we can do induction over outer natural numbers, where well, just recursion, where what we want to construct is some internal natural number, but now we need to use this iota to because this recursor for outer natural numbers only knows about outer types and outer terms. So we use this iota to see this one as an outer type. Okay, then we can use the inner suck and 0 and apply this to n, and we'll get some inner natural number. Precisely, we get some outer term of type iota inner natural numbers. But this will only work in y direction. So if we start with some inner thing, we cannot do the same to get an outer natural number, because we cannot see an outer type as an inner type. So here the answer is that we have something in this direction. But we don't have something in the other direction. And well, more generally, this will be true for all inductive types. We can go from outer to inner, but we cannot go from inner to outer. Okay, because if everything was isomorphic between the inner and outer layers, well, it would not be interesting. to have several levels, but the inner and outer levels can really be different. And well, so maybe we can look at the Preshift model for this. So in the Preshift model, what will inner natural numbers? So let's look at the Preshift model over the syntax. What will inner natural numbers and outer natural numbers be? Preshift over the syntax of our Taifuri. So the terms of inner natural numbers will be the Preshift of terms of type n in this initial level, but terms of the outer natural numbers. So this is really the Preshift of natural numbers, and it's the constant Preshift of natural numbers. So this is just well, these are actual natural numbers. Again, we have a map in one direction, because if we have any natural number, we can get some iteration of suck and 0 in the syntax. But if we have some term of type not in the syntax, to get an actual natural number, we need to evaluate it. And well, this is not possible for all Taifuris, and even when it's possible, we only expect it to be possible in the empty context. So really, we do not expect to get a map in the other direction in that case.
Are there some interesting special cases when we do get a map? Like, what if the inner theory is not the syntax, but the standard model, for example?
Yeah, I don't really want to look at Preshifts over a category of sets. It looks but in that case, yes, probably it will work, because natural numbers of the standard models are just natural numbers, and natural numbers of any Preshift models are also just natural numbers. So in that case, we may get an isomorphism, although something weird may happen if we look at things over empty sets. But yes, if you look at Preshifts over sets, maybe we do have this isomorphism. But I'm not sure. And then, but then there's
and sorry, and if we have this normalization for the inner theory, that's not enough, right?
Well, that's no. I mean, this will be enough in the empty context, but not.
Yeah.
Yeah.
I mean, but the the things in the outer terms of type natural number are also not actual natural numbers, only in the empty context, right? So
well, no, in the pre-shift model they are really just natural numbers.
well, in the empty context,
okay,
right?
yeah,
So,
okay, yeah, they are, yeah. And yeah, but this is a in the empty context and also in any in any representable context. So yeah, that's yeah, okay. At least this is true in any representable context. And then yeah, of course, if we work over some general preshift, this we may get an isomorphism in some cases, I guess.
Question: if I have a context which only has 3 types, then is that always representable or not necessarily?
If you have a context that only has 3 types, I don't understand.
C types, like
context. C types. Okay. Yeah, then yes. If you have, do you mean something like this? For instance, this.
Yes. Or with only
then,
C.
Then yes. Well, in the preshift model, then yes, it will be representable because this will be yeah, essentially in the preshift model. This will be isomorphic to Yoneda. Extended by A, extended by B, where this extension is in C.
But we do not have that iota of A is isomorphic to Yoneda of A because it's not the same thing. Because I mean, this iota has this additional generalization step compared to Yoneda.
Yes, and there's no there's no Yoneda of A here. And you can have some.
I mean, but we know already from the definition of Yoneda that the right-hand side is isomorphic to Yoneda of empty extended with Yoneda of A extended with Yoneda. But we still don't have that iota A is isomorphic to Yoneda of A. Or do we have?
I think we do, and we need to say, so I guess A, and it's not word type of so that's why I'm confused, because so if
yes, that's why we don't have
A, but yeah, actually what happens here is that if we write this, then A has to be some unit of something. So actually this one's already not well typed, but we will have something like this. Because yeah, because this action of unit down types is an isomorphism over contexts of C, and then this is a context of this is and context of C are things that are from unit of something, and this is unit empty. So and then you can extend like this.
But is it well typed to have a iota over Yoneda?
Yes.
I mean, so A prime is a just in tie C, and then Yoneda is in the Prishev model. But
so here A prime is in tie C over here. Well, here it will everything will be in empty context. But okay, in the general case, it will be over some context gamma, and unit of A is in tie what I wrote tie C of Prishev of C over unit of gamma, and iota of unit of A. It will be the same, but we remove VC.
okay, but it's not immediate that unit of A has tie C PSHC type. So maybe
This?
Yeah, so that's something that we have to show, right?
I mean, that's the definition of unit of A, but this was some unit. This is a unit.
I mean, Yoneda is a morphism.
No, but no, I don't think, because Yoneda should return in the usual tie in the Prishev model, because Yoneda is a morphism.
Yeah, so there are two Yonedas. So there is. I guess there's Yoneda, and there is Yoneda composed with iota.
Yeah, but if I have an A prime in tie C, then the Yoneda of A prime returns a normal tie in the Prishev model.
Well, right? This one returns does not return a normal type.
But then it's a different Yoneda. I mean, the usual Yoneda goes from C to Prishev C, but it has to return a normal type in Prishev C.
Well, yeah, but so this is my iota composed with Yoneda.
Yeah, but the iota composed with Yoneda is only well typed if Yoneda returns in tie C. But usually
so split Yoneda into two steps. Like it's a more refined version of Yoneda, where Yoneda doesn't go to the usual Prishev model, but to this tie C and TMC. A type structure in the Prishev model. So it's like it's a better understanding of what Yoneda is actually doing, because the usual Yoneda is the composition of these two steps.
So you say that the usual Yoneda is actually just this composition of Yoneda.
Yeah, I mean the usual Yoneda for types and terms, but for context it's the same. Yeah.
Okay.
Exactly. Okay, so what's next? Yeah, I guess I can look at how we can use this also to specify to specify the type theory in a more direct way. So if okay, so let's say that C is a CWF, and then we look at Preschifs over C. It's now a model of two-level type theory. And maybe type C, and maybe I would say use type C and TMC for the inner level, and type O and TMO for the outer level. And this one has at least pi and sigma. And then we can yeah, and actually in this case, because we also have so we have this iota from type C gamma to type O gamma. But you also have something figured small type C, and this is just in value gamma. And where is it? Yeah. And here we have this these isomorphisms tau, and here we have isomorphisms between TMO type C and type C.
So this is a universe, right?
So, well, it's not exactly a universe, but it's some kind of universe. Well, yeah, I guess it's a universe in outer types for inner types.
Yeah.
So I would, it's very similar to a universe.
But maybe if you have two family structures on a CWF and a morphism between them, can you always do this construction?
No. Yeah, so this is an extension of two-level type theory. We don't always have this.
Mm-hmm.
But we do have it in the Preschifs model.
Mm-hmm.
And we always have this if we have enough universes in the inner level. Mm-hmm. Because then we'll have something. So if you have universes in the inner level, we have type C equivalent to TMC of some universe. And well, so if we have in universes, maybe we want to index this with universe levels. And then this would be terms of type UN. And then this would be the same as outer terms of type eta UN. And so we can say that type C is iota of UN. But then it will be TICN. Now we can say that we have maybe some pi I. So we can try to specify inner pi types, and we can say that we have some pi I of type pi O of A in Stacy and B in pi O of so this will be this will be so A is in Stacy. There we want iota of A basically. Yeah, I don't want to give a name to this isomorphism. And something like this, and this will return in TIC. Yes. And we can continue and define, for instance, lambda I. This is now a small a iota A, and this is iota of B applied to A. Again, we can continue like this and fully specify the inner pi types. This is, and then we can show that C has inner pi types if and only if precious for C has elements like this.
Lambda should return pi, right? So for lambda,
yes. This will be iota pi I. A. Thanks. Yeah, so right, so C has yeah, we can prove that the model C has inner pi types if and only if the Preshift model can be equipped with terms like this. And well, this is nice because now we do not need to we do not need so inner pi types over C. This consists of pi and then some substitution rule, and then lam, and some substitution rule, and up, and so on. And this is nice because now we can skip these substitution rules, and we don't need to care about them. Okay, so what's next? Yeah, and now we get a somehow if we look at the initial model of some two-level type theory, maybe it has a nice syntax, and then you can use this nice syntax to talk about models also of other type theories that are not so I kind of lost my focus. So is there any is there anything about two-level type theory that I may have skipped?
Depending on what we want to talk about. But I mean, if just presenting like two-level type theory and usual semantics, I don't think anything was skipped.
Yeah.
Yeah, so maybe, I don't know, it would be nice to show an example, for example, like defining semi-simplicial types or something like this, which two-level type theory was originally invented for. And in fact, they didn't invent the first version of two-level type theory didn't even think about pre-sheaf models. They just thought about like what kind of extra structure we should add to type theory to be able to express these kind of constructions, which are kind of external but not really. Yeah.
What I don't, because it was also motivated by the semi-simplicial set model. That is some kind of pre-sheaf model, where then the outer layer are just pre-sheaves, and the so just simplicial sets, and the inner layer are fibrant simplicial sets. So it's not. So it is some kind of pre-sheaf model. It's not. Not the kind that I have looked at here.
But I wonder I wonder what's the simplest example. So maybe semi-simplicial types are a simple enough example, but maybe there is something simpler where you need to go external for some time, and yeah.
I'm not sure, because for semi-simplicial types we also need some like extra axioms in the two-level type theory.
No,
what do you mean?
I mean we can define semi-simplicial types for any like depth of unfolding in normal two-level type theory, right? But
no,
we cannot.
Normal type.
Okay, yeah. No. So we can get truncated semi-simplicial types, but we cannot get full semi-simplicial types.
But we only get full semi-simplicial types if we add some cofibrancy condition or something.
Yes. Yeah, but I can.
This is a bit like we can quantify over the truncation level two-level type theory.
Yes. Yeah, I think in Hot there's also lots of cases where we know we can prove that some type is untruncated for every n. Well, no, yeah. So I was just thinking about this free group problem where if we know that subtype okay, but okay, maybe I can talk about semi-simplicial types. So semi-simplicial types in Hot have a sequence of so it's some kind of some definition that starts like this. It's some sigma type or regular type. It starts with some set of points and then some set of lines between any 2 points, and then some set of triangles between any 3 points and 3 lines. Maybe you can give this one as well. There are too many lines. Skip it. But so it's quite easy to see that we can that you can continue the definition. But the question is, can we define S from natural numbers to the universe such that S such that S0 is isomorphic to S0, S1 is isomorphic to sigma x0 x1, S2 is isomorphic to sigma x0 x1 x2, and so on. Well, so this is some kind of object of, and this has some kind of combinatorial structures. So we can see that at every step we have n plus 1 elements of x0 and n choose 2 elements of x1 and so on. So we can try to describe the general definition of Xn this way, but we need to prove some lemmas about so this corresponds to choices of 2 elements among 3 in this case. So here we choose. So we can try to do something that looks at all subsets of the points and add some elements of the corresponding type. This should be X1. But then if you look at subsets, or if you look at subsets with some cardinality, then we need to prove some lemmas about compositions of subsets. Well, not subsets, but finite embeddings or things like that, or increasing embeddings. And then we get into coherence issues, because if we have some something about if you have some some of these increasing embeddings, and then lemmas about their compositions. And then we need some additional lemmas about these lemmas, and it seems at least that we need to prove some infinite amount of lemmas. So it seems that this function cannot be defined so without the uniqueness of identity proofs principle. Well, they cannot be defined at least in hot. Okay, but in some cases we may want to still try to work with this definition, because well, at least externally we can say pick some natural number. We can pick some natural number, let's say 10, and then do something with this. But if we completely unfold this definition up to 10, well, it will be completely it will be much too complicated. So we still want to do something with this. So what we can do is use two-level type theory, and we define instead of this S, some S from external natural numbers into U. And now this is the internal universe. Again, the issue here is that we don't have UIP, and that's the uniqueness of identity proof principle. That says that for every P in ID XX, P is equal to FL of X. But if we look at two-level type theory, and in particular if you look at the Precious model, Precious model over the syntax of hot, this one has UIP for external, for outer identity types. And this means that and you can use this to define S. And we can use this to describe to do this construction. And well, more generally, we can so I mean, it will be quite easy to write some program that outputs a string that corresponds exactly to the unfolding up to n of this definition. And somehow this is exactly what is achieved by using two-level type theory, where we give some program that generates pieces of syntax of inner theory. But then you can also use we can also continue and then prove things about our constructions. So okay, I can try to be a bit more precise and explain where there will be some problem and what is the and try to explain where there will be some problem in the naive attempts to define this. So the idea is that if you want to define this, probably we will define some. Okay, so we'll define some S from natural numbers to the universe. and Sn, well, okay, so S0 will be, well, maybe it's either empty or just a set of points. And S of successor of n, it will be some sigma type of Sn, and then we need to define some Xn. Okay, so this means that at the same time as S, we need to define some X for every natural number from Sn to U. Okay, how should X be defined? Well, it should first collect some points, and then some lines, and then some triangles, and so on. X of n will always, and S will always be something to set. And what should be this something? Should be the boundaries of lines or triangles and so on. Yes, we can try to define the type of boundaries. Of n simplices. But actually, the probably what we will attempt is to define some. Is what we will add some other parameter m, where m is smaller than n or something like this, and then b and s. M will be the type of the boundaries up to type of the simplices of size at most m of the boundaries of n simplices. And well, maybe this is less than or equal. And then instead of b, and then here we'll use we want the full boundary in this X. Okay, so for example, B2, some S will have X0 and X1, and 0 will be the unit type, and then 1 it will be the type of X, Y in X, in X0 times this times this. Like this. And then B22 will be this, and also times X01 and X1, X0, X1, and so on. Okay, so generally we'll have, well, I guess always Bn 0 is equal to top, and then Bn S successor of M. It will be Bn S M times, and here we want to say for every function from fin M to fin N, that is, well, maybe one way to say it is that for every way to choose M elements among N, we want some this S will be some x at smaller than m and some xm, and we want some element of xm at f. We want some element of xm at the boundary restricted to f, at the previous boundary restricted to f. So, for instance, if we look at this instance, xm will be x1, and the restriction to f will restrict the tuple x0, x1, this should be 2, to just x0, x1. Yeah, the issue is how do we define this function? Well, to define this function at the end, this is where we'll get into coherence troubles. But if we have UAP, we can complete the definition by just defining this function, and there's no issue. Yeah, so I don't know if this is yeah, so this is just some combinatorial description of this thing that is
I think time is soon over.
yes.
So I don't know if there are any questions can discuss, or we should also discuss. Okay, what should we do next week? Because we can look at canonicity for time.
I think this will be good.
And I don't know, and what do we do after that? So, okay, maybe we normalization a little bit, but I think we probably covered everything that we planned to cover, no?
Yeah.
Or was there anything else that we wanted? Because in the beginning we discussed what we want. Okay, one other thing that we said was the setoid model, but we also talked about the setoid model a bit, right? We called about families and families model, and
yes,
related model.
Not that much.
Yeah. Mm-hmm. Yeah, but I think the canonicity is important because it's an important meta-theoretic property of theory. And okay, so next week I will talk about canonicity then, and then we'll see. Then we'll discuss.
Will you use gluing or?
No, I think just. No, I think how I would do it is to like look why the direct what goes wrong if I want to prove directly that every term has in the empty context has a normal form. just by induction and the syntax, and then this idea that you need to define a predicate for each type, and then at the base types, the predicate exactly says what you want, and for function space, it says that every term preserves the predicate. So this is this idea of what's this? This is a very old idea. This kind of when you want to prove something, you prove a more general statement or family of statements, and its special case becomes what you wanted. Yeah. So from kind of this intuition, and then just start to do the construction by hand, and yeah. But we'll see. Okay, then thank you.
I will stop the recording.
Yep.